to prove the Moivre's theorem, and the Moivre's theorem basically states that if we have any complex number, which can be written as the modulus times cosine theta plus I sine theta, and we raise it to the power of n, we will get the modulus raised to the power of n and the argument multiplied by n. So we will be proving this using proof by mathematical induction, and first we will need to prove for n equals 1. So we raise the complex number to 1, and it is true for n equals 1, as anything raised to the power of 1 equals that thing itself. Then we need to assume true for n equals k. K is any arbitrary integer, and we just rewrite the exact same thing we wrote for the complex number raised to the power of n. And it is important that we know that k is a positive integer. So the aim is to prove that it is true for n equals k plus 1. So we raise our complex number to the power of k plus 1, and now we can rewrite it in the expanded form to see what we want to arrive at. Now, we can't just say that this is the proof, but this is what we want our final product to be from using principle of mathematical induction. So if we raise the complex number to k plus 1, that will equal the complex number raised to the power of k times the complex number, as anything raised to the power of k plus 1 equals that thing raised to the power of k times that thing. Since we assume true for n equals k, we can use that assumption when doing this proof. Here I'm just rewriting what we are going to be multiplying next. We get r to the power of k plus 1, and then we just need to expand the brackets with the trigonometric functions of cosine and sine. So once we expand, we can see that we will be using compound angle identities to prove the Moivre's theorem. So if we recall, cosine a plus b will equal to cosine a times cosine b minus sine a times sine b. Similarly, sine a plus b will equal to sine a times cosine b plus cosine a times sine b. And we can see that in our expansion of the complex number raised to the power of k plus 1, we get 4 products, which we can arrange into 2 compound angles. And once we do that, we will notice that we arrive at what we wanted to arrive and what we wanted to prove. Theta plus k plus theta can be rearranged to k plus 1 times theta, which is what we visually want to see. Since true for n equals 1, and if true for n equals k, because remember that was an assumption, then it is true for n equals k plus 1, so it is equal to any number plus 1. Therefore, it is true for all n are positive integers, and therefore this is proved by principle of mathematical induction.